So now we're going to look at texturing with example 4.1. Let me run that here, and you can see it's demonstrating how to paint a texture onto our two triangles. And to bring in texturing, we're going to need to be able to load images from files, in this case from a JPEG, and so for that purpose we're adding a new dependency, s2b_image. Now we also have these other two includes filesystem.h and shader_s.h. These provide abstractions for working with the file system for loading files and for encapsulating a shader as a class. I'm not going to cover that. It's not anything specific to OpenGL. It just abstracts around it in a little bit more convenient way. And so now when we load a shader and set it up for use, it's done with this constructor call where you pass in the file path to the vertex shader and then the file path to the fragment shader, and now those are stored in separate files. Before we were just writing them inline as strings, but as your code gets larger, of course, it's better to split them into separate files. It's also advantageous this way because if we want to change our shader code without changing our C++ code, now we don't have to recompile. If I come over here and make a change to my shader code, I just run the executable, and because the shaders are loaded and compiled at runtime, then I don't have to rebuild the executable to change my shader code. So with this exercise, we've cleaned up the boilerplate a little bit. Otherwise, what's new here is now we're working with a texture. And so now in our fragment shader, rather than just taking a solid color and assigning it to every pixel of our polygons, we're going to read a color value from a texture. And two-dimensional textures in GLSL are represented with a type called sampler2D. That's going to be passed into the shader as a uniform, which we're going to have to set up in the C++ side, of course. But once we have our sampler, we can sample from it, we can read values from it with the texture function, specify which sampler, and then the coordinate, which here is an input variable that is going to be passed from the vertex shader, a vec2 for a u and a v value for texture coordinates. And note that this other input variable, our color, is being ignored in the shader. We could just get rid of it. It's a hangover from a previous exercise, and I think it comes into play in a later exercise, so that's why it's here. But we don't really need it, of course. As for the vertex shader, it's getting 3 inputs. Now a third attribute for the UV coordinates of the vertices. So atextCoord here is for this vertex, what is the associated UV attribute? And we're creating 2 outputs that get passed as input to the vertex shader. We set GL position as normal. We're setting our color again like we did before. And we're setting the output variable textCoord. I don't know why he's reconstructing a new vec2 value out of the x and y of atextCoord, because it of course already is a vec2, so we should just be able to write this for the same result. Not sure why it was written that way. This way of course will work. So that's what's going on in our shaders, and now what we need to know is how do we set up on the C++ side, how do we set up this third input? Looking back at the C++ side, you see we have the indices for the 2 triangles because we're going to be using draw elements to draw this time. We could of course just use draw arrays and not use indices, but then we'd have to duplicate some of these vertices within the vertices array, and it's just a little clearer if we don't have to do that. So now we're adding, in addition to the 3 position floats and the 3 color floats, we now for every vertex also have 2 texture floats, the U and the V. So the top right gets 1, 1, the top right of our texture, the bottom right gets 1, 0, the bottom right of the texture. The bottom left of our rectangle is mapped to the bottom left of the texture, 0, 0, and the top left of our rectangle is mapped to the top left of our texture. So for these texture chords, we need to set up the third attribute with GL vertex attrib pointer index 2, an attribute that will have a count of 2 values, because it's just 2 floats, not 3 this time. They're still floats, still don't want to normalize any fixed point values. And the stride between vertices now is 8 times the size of a float because each vertex has 8 values. Notice we have to update that for all the attributes. And the offset to the third attribute is 6 floats in. It's the 6th float within the vertex. So that's our vertex attrib pointer call. Don't forget to enable the vertex attrib array with index 2. This should be a familiar thing by now. We're now just setting up a third attribute as input for the vertex shader, here coming in as atextCoord. But what about the texture? First thing we need to do is create a texture. So we do so with glgen textures, much like we have done with other kinds of objects. We then bind the texture so that certain calls that follow, like this one here, text parameter I, it's going to apply to this texture which is currently bound. And with these calls to text parameter I, the I standing for integer, to distinguish from calls where floats are accepted for parameter values, we're configuring certain parameters of the texture, including the GL texture wrap S value, the GL texture wrap T value, texture min filter, texture mag filter. These are the most essential parameters. What the texture wrap parameters determine is what happens when you try and sample from a value that's out of the range of 0 to 1. Well, here for the S and T dimensions, which correspond to U and V. In different contexts, we say UV for texture coordinates. In other contexts, we say S and T, but they mean basically the same thing. Anyway, we're setting the wrapping policy for both dimensions to be repeat, such that, say, the U coordinate 1.1 would be interpreted as 0.1. 2.1 would also be 0.1. 3.1 would also be 0.1. So with repeat, we're effectively ignoring everything but the fractional component of the value. And this gives the effect of the texture wrapping. And we can see what effect this would have if I were to change these values here. I'll change them to 2. Save, come over here and build the project. Run the program. And now you can see the texture is repeating 4 times. What was just this lower left quadrant stretched over the whole rectangle. Now it's that same thing repeated 4 times because of our wrapping policy of repeat. There are several other options to repeat. I'm not going to go over them here, so you can look those up. But that's what's going on with the wrapping parameters. As for texture min filter and mag filter, min as in minification, mag as in magnification. Min and mag have to do with bitmap levels, which I discussed in a prior video. And linear here refers to bilinear filtering, which is again something I've explained in a prior video. This effectively is determining what happens when our UV chord does not correspond to the precise center of a texel, to an individual color value in the texture. And with bilinear filtering, then the color you get is not a precise match for just that pixel. It's a weighted average of that pixel and its immediate neighbors. Again, this is something I explained in a prior video, and there are many sources that explain the concept, so I'm not going to delve into these details here. Having set the texture parameters, we need to load the actual data into the texture, and so that's going to require reading the JPEG file into an array of bytes, and so that's what this STBI load function is doing. And for this call, it's going to set an int width and an int height, and also the number of channels, though we're not actually going to use this in this case because we know what the number of channels in this image happens to be. It's 3, it's RGB. Upon success, data here will be non-null, otherwise we're going to come down here and print out an error message. But assuming we've successfully read the image, then we're going to call textImage2D. The 0 here specifies the bitmap level we're defining the texture for. Again, bitmaps are a concept I talked about in a prior video. I'm not really going to go into it here. This RGB parameter is saying that the internal format, what we're storing on the GPU side, is going to be in the format of RG and B, red, green, and blue. Then we have the width, the height, and the 0 here is the width of the border for the image. I'm not sure why you would give your textures borders, but that is an option. The second RGB is specifying the format of the data we're reading from data, and unsigned byte specifies the format of each value. In this case, they're unsigned bytes. So with the texture data loaded into our texture object, we call generate bitmap to generate different levels of bitmaps. And I'm pretty sure this step is not required, but you do generally get better results. You get better texturing. Anyway, now we have a texture object ready to use. Last thing, we should deallocate the data that was allocated by STBI. This is no longer needed for our texture object because the data has been copied into the texture object. Lastly, within our rendering loop, nothing here is new. Just make sure that the texture is bound before we draw. Note here this method call on the shader object, on the class encapsulating the shader. The call to use here just sets the program as active by calling GL use program. And very last thing here actually is, well, having now created a texture object, like everything else properly, we should clean it up before we exit. So we should delete the texture. Let's look at the next example, 4.2, textures combined. And now what's happening is that we've loaded 2 textures, and for each pixel we're producing a combination thereof. We're blending between colors of 2 textures for each point on our rectangle. Our vertex shader is unchanged from the prior example, but now the texture shader, we have 2 uniforms, 2 textures, texture 1 and texture 2, And we're going to use the mix function to get an interpolation between these two texture samples. And we're doing so with the value 0.2, meaning that the second one contributes 20% and the first one contributes 80%. And that is how we get the frag color. So now that we're creating two textures, we need two texture handles, texture 1 and texture 2. And we do the whole process we saw before to create texture 1 with container.jpg. And we just do the exact same thing for texture 2 with awesomeface.png. In this case though, notice that it's RGBA. There's an alpha channel, both in the data we're reading from and the texture we're writing to. We want to actually store that alpha channel because if we look at this ping, you'll note that there are some actually transparent pixels. Not the whites of the eyes, but everything around the circle is transparent. Now, aside from creating a second texture, the other thing we have to do differently now is we actually have to set the uniforms. Strangely, in the previous example, we created a uniform variable and created that texture, but we didn't explicitly set the sampler2D uniform value to that texture. Because what happened there is we only had one texture, so implicitly in the shader, it couldn't have been anything else. Here though we have two textures, so we have to set up the uniforms explicitly. And so this call to ourshader.use, that calls GL use program for our shader to make it active so we can set up its uniforms. And here for uniform variable called texture1, we're setting its value to 0. And here this is doing the same thing for texture 2 with the value 1, but here it's using a convenience method of our shader class to do so. So now this means in our fragment shader, texture 1 will have the value 0, texture 2 will have the value 1. So sampler2D, it really is actually just an integer value, but it's an integer value representing one of the texture mapping units. And so when we call texture and specify value 0, it's saying we want to read from the texture mapping unit 0. Now, before we draw, we have to make sure that texture mapping unit 0 is set to our first texture and texture mapping unit 1 is set to our second texture. So that's what these lines do. We're saying make texture mapping unit 0 the active texture and bind texture 1, make texture unit 1 the active texture mapping unit, and then bind our texture 2 handle. If you're wondering, well, what is the maximum number of textures I can use in any one shader? Well, that depends on your hardware and driver, but I believe the minimum required by the OpenGL standard is 16.